Good morning, ladies and gentlemen. It's our privilege to be here. My name is Tan Chen. I'm graduating from a PhD program at University of Pennsylvania. My co-author, Mr. Yefan Zhi, is a second-year PhD student. We're all from Polyhedral Structure Lab in UPenn. Professor Masoud Akbarzadeh is our senior advisor. So today I'm going to introduce you a novel approach, a systematic novel approach that's going to take multi-material additive manufacturing technology to create functionally graded architecture material, which you can translate from one type of material seamlessly into another material. So in contemporary architecture practice, particularly in the masonry buildings, components are often assembled in a layered manner for the ease of construction and installation. For example, this is a very typical residential building, especially in the North American region. So the typical method for the construction is that after stacking the concrete cinder blocks, we're going to add another separate layer of framed thermal insulation in the interior side, or other layers of like a mortar or foam panel and a decorative finish layer in the exterior side. So this contemporary tectonics is pretty straightforward and practical. However, it actually has several potential drawbacks. First one is actually the distinct material interface can weaken the bonding strength, making the architecture component less resilient under extreme conditions, such as high wind load. Potentially, it's creating an urban hazard. And the second is that the installation process can be somehow labor-intensive, involving multiple steps and various crafts. In some cases, it's also toxic. And the third one is actually the design for the ease of construction. Design simplicity are often prioritized to the ease of construction and installation, which limits the design freedom. So while the modern tectonic method is pretty straightforward and functional, we kind of like wondering if if this layered manner can somehow evolve can be converted into a gradient object instead of a layered approach. Is that possible if we can create a gradient spectrum but still retain the functionalities of the architecture components? So therefore, in order to tackle those thermal insulation challenge in the masonry building, we propose this idea of integrated and tailored thermal insulation to reduce the risk of delamination and streamline the labor-intensive installation process, and also enhance the design flexibility. So basically, what we want to do, let's say this is a very conventional load-bearing cinder blocks, which has been widely used as a load-bearing component. And the typical method for improving the thermal insulation is just adding a separate layer of fiberglass or polyurethane as a different layers. However, what we wanted to achieve is actually we wanted to integrate both materials so that I have one load-bearing material can seamlessly transit into a thermal insulation material. And also beyond that, we wanted the integration and the transition can be strategically distributed based on the design demand. To achieve this actually is pretty challenging because the process involves very complicated systematic approach, both from hardware and software. So this idea is actually not quite new. It's actually has been long employed in a similar strategy in the biosystem. Specifically, like let's say in a bone structure. In the bone structure, the outer shell has a more dense region, which is for absorbing the impact, and the inner layers have less dense area, which assure the nutrition transportation. So we wanted to achieve this. Idea by introducing a new fabrication method, which is a multi-material printing system. And this system allows for the precise control and seamlessly transition between materials, and that can enable the components that transfer from high strength, low bearing area to zones that optimize for thermal insulation within a single structure. So to bring this so in the multi-material printing, in the mainstream in the literatures, the method typically are involving using multiple nozzles. But however, this method often result in a distinct material interface that still increases the risk of delamination. In addition to that, the switching between different nozzles, it's actually expanded the production time. So in this case, the single nozzle scheme may be a better solution. We inspired by the microfluid technology in the bioengineering, we kind of like expand this idea, single nozzle scheme, into more practical configurations. By embedding active mixing elements into the system, into the single nozzle. So this is two configurations that we developed it. On the right hand, on the left hand, which is designed for handling construction paste, like concrete and clay. And on the right side is actually designed for handling material like thermoplastic and biopolymers. And we also built these functional printers based on those aforementioned two configurations in order to handle different types of material. The multi-paste printer, which is on the left side, was used to validate the functionality and performance of the proposed integrated tailored thermal insulation with construction paste in our research. Meanwhile, the multi-filament printer will be utilized for iterating the final design and prototyping. And also, we developed this in-house PCB, which enables intricate intricate stepper motor control, which mainly managing the rotational speed and torque of each stepper motor that get involved in the system. And the system actually allows us to control up to 8 stepper motors, and also enabling simultaneously printing up to 4 distinct materials in one printing process.
So I'll briefly introduce the software side. So we call a certain mixture of several filaments or pastes a tool, and every tool is defined and stored in the beginning of the G code. And whenever we print a line consisting of multiple tools, we start with activating the first tool, move a little bit and print some of them, and switch tool. So we have a very standardized G code template that's created and taken into the machine. And this generation of the G code is also automated in our research. We have a in-house developed tool called Ovenbird. It supports single material and multi-material printing, and has a continuous printing feature, and it's available on Food4Rhino. So it allows very different design strategies when you try to code the multi-materialness, and you can always optimize and visualize and do a lot of post-processing. So we have several upcoming papers about this, and with that I'll hand it back to Tim.
Thank you. I strongly recommend everyone to take a look at our plugin in the Food4Rhino website by scanning this QR code. And beyond that, through the integration of the hardware and software developments, we actually achieved 2 primary features in our system, which is gradient material transition. You can see in the video, it's actually transit from one to another seamlessly, and we can achieve up to 4 materials so far. And also for the gradient material, programmable material composition, we actually just input 2 different colors of filaments. It actually can blend into basically theoretically infinite number of new mixture by regulating the rotational speed of fatting motor. So this is the girl is earring, pure earring, 3D printed by our machine. So we began validating the functionality and performance of integrated and tailored thermal insulation using our multi-paste printer. Primarily we use 2 types of material, the red stoneware clay and the white diatomaceous earth. The stoneware clay serves as a conventional load-bearing material due to its high density, while the diatom meshes earth with its high porosity offers superior thermal insulation property. Just for information, diatom meshes earth is actually a nature occurring rock composed primarily of fossilized hard shell edging. So we test the programmable material composition feature by adjusting the rotational speed of the motor, which supplies the material. In this controlled material blends, producing a sample ranging from 100% of diatom meshes to the mixture like 90% of diatom with 10% of clay and so on, and down to 10% diatom with 90% of clay. You can tell the gradient material composition changing by the color. And also, once the material composition is programmable, actually the material properties can also be tailored. We test this by placing these samples with varying composition of red clay and diatom meshes earth on a heating bed at 40 degrees Celsius for 1 hour. And we use the thermal camera to observe each samples. In the thermal image, you can tell that the lighter color actually indicating the higher temperature, also indicating a higher thermal conductivity, and the darker color indicating lower temperature, while the material has a lower thermal conductivity. So we can program, at this point, we can program the material property by programming the material composition. And also we also print the both paste material in 2D and 3D manner to verify our system's printability and the level of the fidelity that we can achieve. And eventually we print this 20 by 20 by 20 cubic geometry centimeter, featuring the transition from diatom meshes earth to clay. And this box was placed in a kiln set at 100 degrees Celsius for 1 hour and to test its thermal performance. So this is the picture taken by the thermal camera. The material itself has a transition material embedded inside within one continuous geometry. And the thermal performance can actually be programmed by our design and the material design. So this is another test we did. Designed thermal box with 4 corners designed to be a low bearing and the partition wall to be thermal insulation. So we test this compressive strength with a hydraulic press. The compressive strength of this thermal box reaches to 2.5 kilonewton, which is a lot, because the box is like handful size. And having verified the proposed idea, integrated and tailored thermal insulation is both functional and achievable in our system, we transit from using the multi-paste printer to the multi-filament printer and enable us to design prototype masonry architecture components for the further demonstration of the concept. And in this stage, we use the wooden fiber fused filament to the load bearing zone, and also use the forming PLA to the thermal insulation zone. Because you can see that in the microstructure, the forming lightweight PLA has a higher porosity. So the design is like this. We designed the masonry wall beginning with the stress analysis using Karamba and applying the 6 vertical loads supported by 2 base points. And this analysis identified the principal stress line with blue indicating the compression and red showing the tension. Based on these stress patterns, a rib structure is generated. So we strategically distribute the wood fiber fused PLA at where it has the higher stress, where it has a higher strength. And also we distribute the lightweight forming PLA at the in between those structural rib. And in terms of the two-pass design, the two-pass design begins by identifying the load-bearing components to absorb vertical loads. And we offset the profile at folds to enhance the structural strength, creating the continuous two-pass. And the final wall components transition seamlessly between wood fiber fused filaments to lightweight forming PLA. We have several samples. If we can, yeah. So basically, what we can do is we use the method to print all the samples, wall pieces, then we assemble them together. And at the same time, we also incorporate non-planar printing into the system so that the printing direction can be better aligned with the force flow. So we, after printing all the pieces, we assemble this small-scale wall, and we expose this finished wall piece under the sunlight, with exterior side facing to the south, which is this side. For 1 hour, the ambient temperature at the time was like 32 degrees Celsius. So this is the exterior side of the wall after 1 hour exposing the sunlight. You can see that from the thermal map. The average temperature of the surface is like 32 degrees Celsius, while the interior side has only like 25 degrees Celsius. And this is the comparison between the interior side and exterior side. You can see the performance is just like what we expected. So this is the project we have done so far. We have several upcoming publications going to debrief all this technical aspect of those printers and the design. And we do want to express our special thanks to our advisor, Professor Masoud Akhtarzadeh, by printing his portrait. And our self-portrait, and also the entire lab's portrait. And we do want to acknowledge that this research is supported by United States National Science Foundation, Future Manufacturing grant, and also Department of Energy. So you guys are welcome to scan this QR code to follow our